A client met his banker to discuss opening a restaurant in a busy airport. In us, he found a partner that understood the importance of reaching for the sky. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac.
When you visit Arizona, time is measured in moments, not minutes. Like the moment your work stress disappears as you kayak through the canyons. Or the moment you discover the life-changing effects of prickly pear chocolate. But nothing beats the moment you see the Grand Canyon for the very first time. Visit a new state of mind. Learn more at hereyouareaz.com.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast we call Space Nuts. And I'm Andrew Dunkley. It's lovely to be with you once again, and joining me from the Australian Astronomical Observatory is Fred Watson. Hello, Fred.
How are you doing, Andrew?
I am jet lagged to hell, to be honest. I've just, people wouldn't have noticed because we crammed before I went and got some episodes together, but I've been overseas for 3 weeks visiting Europe, and the jet lag, like it's a 22-hour flight home, and I can't sleep at the right time of the day, basically. It's a horrible feeling. It's almost like having a cold, Fred.
Yeah, that's right. I'm going to pick you up as well, Andrew, on something you've just said, which is that I'm Fred Watson from the Australian Astronomical Observatory, which is perfectly true this week. No, it's still the same.
Oh, still the same.
Next week it won't be.
Right. I knew it was coming up.
We might talk about that next week.
So that's the last time I'll ever have to make that reference by the sound of it.
I'm pretty sure most people will just say Fred Watson from the Australian Astronomical Observatory.
Yeah, we in the journalistic industry are a bit slow on the uptake sometimes.
It's all right.
Now, today, Fred, jet lag and colds aside, we're going to dedicate the whole program to listener questions. We've got a bit of catching up to do, which is going to be a lot of fun because these are obviously things that people are really keen to know more about. And so we're going to focus on a question about the Moon, Venus, Jupiter and Saturn to start off with, an issue regarding gravity waves, dark energy, and a Big Bang theory from our audience, which I'm sure you'll find easy to answer. But first of all, we've got a question from Rich, who is in Sydney. He said, I've just been watching the Planet Show in Sydney on the beautiful night and began wondering why the Moon, Venus, Jupiter and Saturn are travelling along the same plane. Very, very good question.
It's a fantastic question. And perhaps I can just, preface the comments with the fact that all of the questions that we receive from Space Nuts listeners are brilliant. They're all right on the money. Our audience is clearly a thinking group of people who hit on exactly the things that people should be asking about. And Rich is right on the money with this one. And it's true, just at the moment, Andrew, and certainly from here in the Southern Hemisphere, we've got this beautiful display in the night sky, with Venus setting in the west in the early evening. Jupiter is high in the eastern sky. Saturn is not very far below it. And if you wait for another half hour or so till the mid-evening, you get Mars rising. And if the moon's in the sky, which of course it is every month as it goes around the Earth in its orbit, what you can notice, and Rich has clearly noticed this, is that basically they're all in the same line. The planets string out along a path through the sky. The moon's pretty well in the same place. It deviates a little bit, but not by very much. And it turns out that path is also the same line that the sun traces out in its annual movement through the sky.
Oh, right.
So what that's telling you is that, yes, the planets, at least the ones we've mentioned, Venus, Jupiter, Saturn, and Mars, basically all sit in the same plane, and it's the same plane as the Earth sits in its orbit.
I was going
as
to
well.
say, how could the moon be in the same plane if Earth isn't? But obviously
That's right.
it is.
Yeah, that's right. Actually, the moon's orbit is tilted slightly. It's tilted at about 5 degrees to the Earth's orbit, but it's not very much. Why is it so? Just to give you the technical term, that line in the sky that the sun follows and that the planets and the moon stick fairly closely to is called the ecliptic. That's the technical name for it. It's always been known as the ecliptic. I don't know why. I should check up where that name comes from. But the ecliptic is the path of the sun through the sky, and basically is also the path of the planets as well. Let's just shift our viewpoint for a minute. Sorry, I've just been plugging my laptop in because I just realised it's about to run out on battery. So it's all done now. We're all okay. We'll keep going. Shift our viewpoint from Rich's viewpoint, standing on the surface of the Earth, and well done, Rich, for spotting that and for looking at the planets. It's a fantastic thing to do. Let's shift our viewpoint to outside the solar system, kind of looking inwards. And what you get then is the picture that I guess we all have in our heads, that there is the sun in the middle, and then the planets follow roughly circular orbits. Most of them are elongated to a greater or lesser extent, but they're fairly near to being circles. But they all lie in more or less the same plane. Venus and Mercury are the most tilted ones, but they're not tilted by all that much. The other planets sit in a plane that is very similar to the plane that the Earth moves around in. And that seems like really quite an extraordinary thing. You know, you might imagine a solar system in which the planets are all buzzing around like moths around a lamp. They're all in different sort of trajectories. But we instead have a very well-behaved solar system that's not like that at all. Everything's flat. And it all comes down to the way solar systems are formed. And in fact, this is one of the principal pieces of information that feeds into theories that of how solar systems like ours originate, the fact that they are all lying in the same plane. And another point that is worth mentioning is that they all go around in the same direction. All the major planets go in an anti-clockwise direction as seen from above the Earth's North Pole. So that's the sort of predominant direction. Actually, the sun rotates in that direction too, and most of the planets do. Not all of them, but most of them rotate in that same anti-clockwise fashion. So what you're seeing here is basically a gigantic cosmic fossil. And the fossil is a fossil of the rotation of the gas cloud from which the sun and the planets originally formed.
Right.
So if you think of a big blob of gas and dust, and that's more or less the way the picture that we have of the earliest stages in the formation of the solar system, a blob of gas and dust, a very large one, of course. It's a bit more complicated than that because solar systems like ours don't form alone. So that blob of gas and dust was probably embedded in a much bigger cloud of gas and dust, which was also seeing other blobs forming. So the sun almost certainly formed at the same time as other similar solar systems. Where they are now, we don't know, by the way. That's another interesting story that I think we've touched on in the past. Anyway, this blob of gas and dust collapses under its own gravity as the volume that it occupies gets smaller. The temperature goes up because it's being compressed in just the same way as the air in a bicycle pump. When it's compressed, it gets warmer. And eventually, the gas cloud collapses to a central region, which is so hot that nuclear fusion starts happening and you get the formation of a star, namely the sun. So that's basically the origin of the sun, is through compression, raising the temperature, nuclear fusion taking place, and it starts shining. But the dusty material and the sort of residue of the gas collapses not into a central point, but into a disk. And the reason why it does that is that because by the time you get to the dusty regions sort of collapsing, the sort of embryonic rotation of this dust cloud and gas cloud has speeded up so that as you compress this stuff, there is something called the conservation of angular momentum. And what it means is that if something gets smaller, if it's rotating, it rotates faster. And, it's the classic experiment that you can do sitting on an office chair, rotating one, spin yourself around. You've got to make sure your colleagues are somewhere else first. Spin yourself around with your legs out as far as they'll stretch, and then pull your legs in, bend your knees to pull your legs in, and you'll speed up.
I was thinking more of watching a ballerina, but yeah, whatever.
Your mind is far more elegant than mine in things like that.
But it's the same theory.
Yeah, it is. That's right. Oh, somebody on ice skates. That's the other one.
Yes, exactly.
They pull themselves in and they spin up. And it's because of the conservation of angular momentum. So the solar system, the baby solar system did the same thing. And a consequence of that is that this dust and, residual gas, which is going to be the planets, that forms into a disk. You get what we in the trade call a protoplanetary disk. And it's within that disk that the planets themselves form. By a process called accretion, bits and pieces sticking together. They also crash into one another and knock things apart as well. But overall, the process builds planets rather than destroys them. And so we wind up with a situation today with 8 planets in orbit around a star, but all more or less lying in the same plane.
Okay, there it is. So it actually is more normal than we probably would have imagined.
That's right. And in fact, most of the solar systems that we observe now, indirectly, of course, usually by planets transiting across their parent stars, these are ones in interstellar space. Most of them seem to be in the same situation, that their planets lie more or less in the same plane.
There it is. It's just cause and effect, Rich, by the sound of it.
Yeah, but a great question.
A very good question, and I hope you enjoyed your 10 minutes of fame and are richer for the experience.
Oh, ho, ho.
Boom, boom. Before we get off planets, very hard to see stars and planets in Northern Europe at the moment because of the minimal amount of night.
Darkness, that's right.
I couldn't believe it. When we were in Amsterdam, it was 11 p.m. before it actually started getting dark.
Yeah.
And I've never experienced that before because in Australia we don't have that kind of light. But it's extraordinary.
It's actually quite charming in its own way.
It is very.
Of course, the further north you go, the longer the twilight lasts.
Yeah, well, that's the northest I've ever been, and it threw me for a bit of a spin. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
And we're dedicating this episode of Space Nuts to questions from the audience. We've got a few to get through, and we've got one now from Kerry Ellis. Hi, Kerry. Great show, Fred and Andrew. Oh, well, you must have only heard one of them. How was it possible to distinguish between gravity waves created between merging black holes and neutron stars? We've talked about this before and how gravity waves are formed by different events. Yeah, it's a good question on how to separate the events in terms of what's going on.
It is, and it's a great question, and I think the answer is pretty great as well. So let's get the terminology right. Gravity waves are something that occur in the Earth's atmosphere. What we're talking about here is gravitational waves. And I know it sounds like this comes straight from Pedant's Corner, which it does, because that's where I live, as all astronomers do. But yeah, gravitational waves are the ones that are caused by a vibration of space-time itself, caused by accelerating massive events. Gravity waves are themselves very interesting, actually, because you often get gravity wave clouds forming. It's why we get, sometimes you see clouds which are in a very, very regular pattern in the sky. And that's because the atmosphere has these gravity waves in it, but they're different from gravitational waves. There you go.
Okay, we've cleared that up. Important minor point.
It is. So gravitational waves predicted by Albert Einstein as a result of his general theory of relativity in 1916. What he said was that because mass distorts space, then if you've got accelerations of these masses, it will set up vibrations in space, and they will be transmitted through space as waves in nothing, really. They're waves in space-time.
So would it be fair to say, just as a basic analysis, that it's the same as disturbing the water by rowing a boat?
Yeah, or dropping a pebble in or something like that. Yeah. You know, if you throw a pebble into a pool, you see these waves spreading outwards. And that is a very crude analog of a gravitational wave, because they certainly radiate outwards in all directions, like the wave of the water.
So mine was cruder than yours in terms of theory.
The waves are actually significantly different in form, but the important thing is they do travel at the speed of light, and that was predicted by Einstein and has now been demonstrated categorically by some of the experiments. So fast forward 100 years from Einstein, and we now have the capability to detect these things. They've been sought for decades, but it's only with the exquisite sensitivity that some of the new instruments have that we can actually see gravitational waves as they pass through, as they sort of wash over the Earth. It's basically a pair of devices which collectively are known as LIGO, a Large Interferometric Gravitational Wave Observatory in the United States, and another one called Virgo, which is in Italy, which is now on stream as well. And what that does is that these machines basically sense the movement of large masses in response to the fact that a gravity wave is passing through the Earth. In fact, what happens is the masses stay put, and the Earth itself vibrates slightly because it's following the wave. The amount of movement of these things is just unbelievably small. The figure I have in my head is 1/10,000th of the diameter of a proton.
Gosh.
It's just, it's ridiculously small, but the sensitivity now exists with these what are called long baseline interferometers. They're things that use the wave nature of light to sense these tiny movements. They can actually detect that, and it has already happened. And in fact, I think there are something like 5 or 6 detections that have been made, and most of them still being analysed. I think there are 3 or 4 that have been widely touted. And as Kerry says, they refer to colliding objects, and in fact 2 distinct colliding objects, types of colliding objects, merging black holes and merging neutron stars. Now, neutron stars are, as the name suggests, they're stars, but they're the last thing a star can be before it becomes a black hole, because they're stars which have collapsed to an incredibly high density, billions of grams per cc, in fact, probably more than billions. And that is because the only thing that stops them collapsing into a black hole is the outward pressure of the neutrons themselves in the star. So what you've got in a neutron star is something the size of a city in diameter, but with the mass of the sun in it.
That's just hard to comprehend.
Hard to comprehend.
Yeah.
That's right. If it had been a bit more massive to start,
the only thing that has that kind of mass that I'm aware of is Dutch chocolate, because I ate a lot of it.
Yeah, there's some good stuff among the Dutch chocolate.
Yes.
Yeah.
Okay, so
yeah, if it had been a more massive object to start with, the neutron star would actually have just kept going and collapsed into a black hole. But they are a distinct category of objects. So, all right, black holes are, that things that have collapsed basically to nothing, to an infinitesimal point, but they still have mass. So, how can you tell the difference?
Yep.
And the answer is the way they behave. So, black holes are more massive by definition than neutron stars, because neutron stars haven't had enough mass to make a black hole. So if you've got two black holes that merge, they don't just slam together. What they do is they sort of pirouette around one another. And that, so they basically approach each other and basically go into orbit around their common center of gravity. Mm-hmm. And as they get closer in this long drawn-out collision, they spin faster and faster. So these collisions can take millions or billions of years, Andrew, but it's only in the last few seconds or milliseconds that these things are spinning fast enough that they send out a gravitational disturbance that we can detect. So they spin with ever-increasing speed, and so what you've got there is masses being accelerated, because the spin is a form of acceleration, and that sets up the gravitational wave. But what it means is you only see the gravitational wave in the last few seconds or so of that spin up before the collision, when it disappears, because there's no more masses being accelerated. So you've got this curious wave that's set up in space that starts off relatively slowly and then gets more and more frequent, so the frequency increases, and eventually it just stops. And we call that the chirp. And the reason for that is that if you played it through a loudspeaker, you need a lot of amplification, but if you do that, it's a chirp. It goes, whoop, kind of like that. My impression of a chirp.
Good enough.
Want me to do it again?
Yep.
Whoop. And it's because it's a low frequency getting higher very rapidly and then disappearing.
Yep.
So to cut to the chase, what's the difference between black holes and neutron stars? The same sort of thing happens in neutron stars, but their masses are lower, and so their spin-up time is shorter. So their chirp is a much longer, and it goes on for minutes, because you can detect it, but it takes longer before you get to that cutoff point where the two objects have merged. The scientists who've done this work are incredible. What they can do is they can look at the fine details of this waveform that they get from the LIGO and Virgo interferometers, and then model that. So they can tell exactly what the masses of the two objects are, and also what the combined mass is at the end of it. And the combined mass is always less than the sum of the two masses, because some of that mass has been converted directly to energy. You'll remember E equals mc squared. That's the link between energy and mass. So some of the mass is lost as energy, and that's the gravitational wave itself.
Okay. Very, very interesting. And now that they've got models to identify what's happening, what do we do if a new gravitational wave's detected and it doesn't fit into either model?
Yeah, exactly. That's what people are looking for. And because that's the whole thrust of modern physics, Andrew, is to look for holes in relativity. And by that I mean gaps or things that don't seem to make sense, because that could open up the way to new physics, new physical processes, which we think we need to explain we think we need to invoke to explain the things we're going to talk about next.
Okay. All right. That was your question, Kerry. Hope we adequately answered it. Yeah, it's one of those things. It's a work in progress, gravitational waves, but they're making progress, definitely. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
3, 2, 1.
Space Nuts.
Finally, Fred, we are not dissimilar to the previous topic, as you said. We're going to merge two questions. Hopefully not to create a gravitational wave, but the reason is they kind of work with each other. This first one's from Sarith Pereira. Hi, Sarith. Nice to hear from you. I'm another nut addicted to space nuts, aren't we all? I have a question for Dr. Watson. Dr. Watson. Anyway, we often hear that we have to look back 14 billion years to see the Big Bang. But the Big Bang happened in space and time, which since then expanded to where we are now. So in essence, the Big Bang is happening here, there and everywhere. It's confusing. Yes, it is. Now, second question comes from Scott Appleby. Hey guys, love the show. Been binge listening to catch up. My wife keeps telling me to get a life. Yes, our respective partners are saying exactly the same thing for some reason. Just a theory about the Big Bang. I know it can't be proven at the moment. Just running through my mind, is it possible it all came about from a build-up of dark matter, which ended up under extreme pressure, forcing it to explode, creating the Big Bang and ejecting dark matter and other matter out? Could it be dark matter expanding the universe? Just a thought from a tradie. I'm probably wrong, but just been thinking about it for a while. Two very insightful and closely related questions, Fred.
Indeed, and they're both great questions. So,
and the answer is no, and we'll see you next week. I know I've done that joke before, but I love it.
All right, let's look at Sarah's question first. It's really actually not so much a question as a statement of the way we think things are, and Sarah is right on the money there. We have to look back 14 billion years to see the Big Bang. And it's true, we can still see it in the sense that as you look out into space, you're looking further back in time. And eventually, we look so far back in time that we see a time when the universe was still glowing. And so that, to us, appears as a wall of radiation, which is effectively 13.8 billion light years away. It's now radio radiation rather than blindingly white light, which it would have been when it was emitted. The reason why it's radio radiation is because, indeed, the universe has expanded more than 1,000 times since that radiation was emitted. So it's been stretched by more than 1,000 times. I think it's about 1,300 times, in fact, and it's now a microwave radiation rather than radio waves. But Sarah's point is well made, because the Big Bang, as we understand it, happened in what's called a singularity. And we've kind of touched on this already, because a black hole is a singularity. It's a point in space where the density is infinite. So the Big Bang was the mother of all points in space where the density was infinite. What brought it into being, we don't know. What made it expand, we don't know. We know that for the first gazillionth of a second, it expanded at a huge rate by a factor of more than 10 to the power 50, a colossal amount. But the point that Sareth makes is right on the money. It was all a long time ago. Everything was in a single point. So the Big Bang happened everywhere. And that's sort of counterintuitive to us, because when we think of something exploding, we always think of, we put ourselves outside the explosion, fortunately, and imagine everything starting off from a single point and blasting outwards. So there's a single point that you can identify in an explosion like that. But in the exploding or the expanding universe, the bottom line is that the whole universe was wrapped up in that single point. So space has been expanding since that instant. And I think it is a confusing thing, but the main thing to remember is that the expansion of the universe is actually one of the easiest observations to make, but it's kind of the only one we can make. All we can see is that wherever we look, things are racing away from us, and that tells you that it's an expansion, because it's, the faster they race away, the further away they are. But also, when we look at the universe, it's more or less the same in all directions. So that tells you it's got what we would call spherical symmetry. It's the technical term is isotropic. It basically looks as though the universe is spherical. And they're really the only observations we can make. So that is the best we can do, knowing, though, that at one time everything was probably at a single point. So how does Scott's question then relate to that? And it's a great idea, actually. What Scott has introduced is one of the big unknowns in astronomy at the moment, which is this stuff called dark matter. Dark matter is something we know exists because we see its gravitational effect on other objects, but it eludes detection by any normal means. It's not opaque. It doesn't interact with normal atoms. It doesn't interact with light or radiation. All it does is has gravity, and we basically don't know what it is. The evidence since the 1990s has been that this is some form of subatomic particle, something a bit like a proton or a neutron, but much more massive because it outweighs normal matter by 5 to 1. And that's why physicists are looking for alternative theories of reality that might extend the theory of relativity, because there are some ideas that suggest that there are particles in a framework that you might call, that they do call supersymmetry. And by that I mean a hidden kind of reality in the universe that for some reason we can't detect easily. Supersymmetry says that all normal particles that we can detect have their equivalent supersymmetric particles, which are much more massive, but which are somehow hidden from us, possibly because they're in higher dimensions. And there are two really good candidates among the supersymmetric particles for dark matter. One is called an axion, the other is called a neutralino. They would both fit the bill if we could prove that they exist, but we can't at the moment. So is the pressure of dark matter what caused the expansion? That's Scott's question. The answer is probably not. We think the energy of the Big Bang is independent of the contents. Clearly, they are related because when the Big Bang happened, the universe was pure energy, but that energy sort of condensed into matter very early on. In fact, in the history of the universe, it turned into subatomic particles rather than just photons, which are particles of electromagnetic energy. Particles of light, in fact. The normal matter particles and the dark matter particles came into existence very early on in the universe, and we actually think the dark matter played an incredibly important role in forming galaxies because the dark matter condensed first into or collapsed first into the nuclei of these galaxies, and stars and galaxies formed probably as a result of dark matter. So dark matter's natural propensity is to collapse under gravity rather than to push things apart in the expansion. That pushing apart is something that comes from another of the great mysteries at the moment, and that's dark energy. And dark energy, as we've known since 1998, is causing the universe to expand ever more rapidly. So the expanding universe clearly is linked to dark energy. We have even less idea, Andrew, what dark energy is than dark matter. We've at least got some clues about dark matter. Dark energy is very, very sparing in giving away any clues as to what it really is. I hope we'll find out. And I hope when we do, you and I will talk about it on Space Nuts.
I do too. And just a side question. Is it frustrating for you and your colleagues to have knowledge of the existence of dark matter and dark energy and not be able to explain it? Or is it exciting because there's something to try and figure out?
Yeah, it's the latter, without question. But one thing that I think it's fair to say all physicists have at the back of their minds is, okay, what if we've got it completely wrong? What if the fact that these things look as though the dark matter looks as though it's got gravity, what if that is some sort of illusion that's leading us up the wrong path? But having said that, all the experiments that have been done, all the evidence that's been observed from space, and that's where most of the evidence about dark matter comes from, seems to demonstrate that no, we've got the right picture, that dark matter actually does exist, that it's not something breaking down in our understanding of gravity or anything like that. It is actually a real entity. So whilst you can never be complacent, we think we're on the right track, and it's very exciting not knowing what it is, because one day somebody's going to find out.
Yeah, and it may well be one of those accidental discoveries which would make it even more exciting, I think. I don't care how we find out, but it might be a mistake. You just, I'm looking for something else, and oh, hang on, that's dark energy.
That could happen. That's right.
All right. Thank you to Sareth and Scott for those wonderful questions. I'm pretty sure they live next door to each other. It was a conspiracy. But no, we appreciate the feedback. And of course, we do encourage you to send your questions in. We have, I think, answered a majority. I don't think we've got to all of them, and we may have lost one or two because we take them on 3 different platforms. So sometimes they just whiz past us. But if we've missed a question and you're really keen to get the answer, send it again. More than happy to help. You can do that via Facebook, Twitter, through bytes.com, and somewhere else, I don't know. You'll find it. I don't know where it is. But thank you as always, Fred.
It's a great pleasure, Andrew. Good to talk to you. And next week, I will be talking to you from the Department of Industry, Innovation and Science. Which
means if anyone wants to complain about the missing questions and answers, you can send your letter to Fred Watson, care of the AAO. Because it won't exist next week, we won't have to do anything about it.
Right.
Thank you, Fred.
Great talks. Speak again soon, Andrew.
Okay. Fred Watson from the Australian Astronomical Observatory. And from me, Andrew Dunkley, thanks as always for listening. And we'll talk to you again real soon on Space Nuts.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.